Hello and welcome to part 3 of what I've learned so far about event sourcing in a microservices environment. As we've said in the previous video, the presentation is most suitable for developers with design experience, particularly in microservice environments, and we've created this presentation because when I started looking into communication between microservices and event sourcing, I found a lot of contradictory information and differing opinions. So this is a distillation of everything I've learned from sources that I came to trust and subsequently put into practice to prove that it works. You may have already watched parts 1 and 2, covering the foundational principles of CQRS and event sourcing. This 5-minute video talks about how we handle concurrency in the event stream and a summary of a typical architecture, and the following presentation demonstrates event sourcing in practice, including a note on choreography versus orchestration. So, let's talk about concurrency. What do we do if we're in the middle of applying events from Command A when Command B also wants to operate on the same aggregate route? For example, Command A has retrieved the past events from the event store and hydrated the aggregate route. Command A has been applied to the hydrated aggregate route, and based on the state of the aggregate route, a new event has been created, but we have not yet appended the new events to the event store. Then, Command B is received for the same aggregate route, which then hydrates another copy of that aggregate route, so it is now in the same state as before the events from Command A were created. Before Command B is completed, Command A's new events are appended to the event store. Now, Command B also generates events, different events, but they cannot be applied to the event store because Command B might have had a different outcome if it had known about the latest events resulting from Command A. If the new events are applied to the event store, they might cause the aggregate route to be in an invalid state. For example, if Command A had closed the account, further events, such as withdrawal and payment, may make no sense. One solution is to lock the event store, but this is inefficient and might prevent other aggregate routes from being updated or read. The most common solution is optimistic locking. Each event in the event stream for an aggregate route has an incrementing number, and new events are only applied if the sequence is as expected. New events are only appended to the event store if the first new event has an expected position of 1 greater than the last event in the event store. Otherwise, the command fails. Combining everything we've learned so far, I found a typical architecture that works well. The players involved in a typical architecture are the command handler, which receives a command and passes it to the correct aggregate route, the aggregate route repository, which handles the boilerplate code of retrieving and saving the events for the aggregate route from the event store, and creating a blank aggregate route, the event store, which stores the stream of events for the aggregate routes, and the aggregate route itself, i.e. the domain model, which receives the commands, creates events, and applies those events to itself to mutate its state, and inside there lives the business logic too. So the first thing that happens is the command handler asks the aggregate route repository for an aggregate route referencing the ID of the aggregate route that it requires. The aggregate route repository then retrieves the events for that aggregate route from the event store. The aggregate route repository then creates a blank aggregate route and sends the retrieved events to the newly created blank aggregate route, which then applies events to itself. So then a rehydrated aggregate route is returned to the command handler. The command handler then sends the new command to the aggregate route, and then based on the business logic, the aggregate route creates new events and applies those events to itself to mutate its state. The command handler then saves the updated aggregate route by calling the aggregate route repository. From that aggregate route, the aggregate route repository gets the ID of the aggregate route, any unsaved events or new events, and the last known position in the event store stream. The aggregate route repository then attempts to save those unsaved events to the event store. If the event stream position of the first new event to be appended to the event stream is 1 greater than the last event in the event stream, then saving is successful. Otherwise, another command has retrieved the events from the event store, created a new event and appended it before this command has finished, and so this command fails. If you have any more questions, please feel free to email me directly, or get in touch with Triad via the links shown. Thank you for watching this short video. Up next is the final video, an example of putting everything we've learnt so far into practice.